My name is Fred Kim. I'm an application engineer for HBM nCode, and my email address is here if you need anything. After this presentation, don't hesitate to drop me a line. We're going to spend the next 30 minutes or so discussing time frequency analysis in GlyphWorks, and also put emphasis on some new features in GlyphWorks 10, the latest release that was just issued a week or so ago. So in terms of the content, the agenda, we'll review quickly the time domain analysis and the frequency domain analysis before going into the joint time frequency analysis. Time domain is typical of transient signals. We want to make sure that the signal is correct, and we want to extract some amplitude-based information from the signal. Frequency-based methods are traditionally being used for stationary type signals. So joint time frequency analysis will give us information from both domains into one display, which is quite interesting. We'll see how and why in a few minutes. So this presentation will be interlaced with some demos of the software, so that you can see it live. And again, I'll just highlight the new features in version 10 of GlyphWorks. So let's start with the time domain analysis first thing. It is crucial. I think it deserves a few slides simply because anytime we do some analysis, whether it's time frequency or any type of analysis, we always start from the measurement, right? Something coming from the sensor, and it's always given in the form of a time domain signal. So let's have a look at what GlyphWorks is capable of in terms of signal processing. So we've got in GlyphWorks we've got a time series calculator to create a new channel based on some existing measured channels. We have filtering capabilities, resampling capabilities. We can extract sections of a signal and concatenate other signals. In terms of statistics, we have global statistics such as mean, standard deviation, max, min, but also higher order statistics like skewness, kurtosis, crest factor, etc. And these statistics are also available in a mobile fashion. Like you wanna do running statistics. You wanna see a trend, how my standard deviation is moving with time, or how my RMS or mean value is moving with time. So that's what we call running statistics. Still in the statistical domain, we've got probability density functions that will tell you whether the signal is Gaussian, etc. Similarly, we've got time at level or point counts at various levels, so that these are histograms. Another very typical histogram we propose is the rain flow cycle counting histogram that fatiguers, people doing fatigue analysis are very familiarized with. The graphical editor is something really interesting in GlyphWorks. You can select a section of a signal, interactively, graphically, and by right-clicking on it, decide what you want to do. So you may want to move a spike down to the level of the correct signal, or you may want to correct some drifts, or even apply a filter locally on the signal. That's very interesting. Also, we've got means to automatically detect spikes, outliers in general. So spikes, drifts, flat lines, saturation, etc. That's very useful to have something automatic that just quickly tells you whether your signal seems correct or not. Often when signals are very large, very long, we like to apply some data reduction to extract only the useful information. So most of the time, by data reduction, we mean histograms, level crossing histograms, or transition Markov, right, matrices, or joint probability density functions. So we've got all sorts of signal data reduction capabilities like this. Now, in terms of fatigue analysis, that's our bread and butter in nCode. So we've got means to compute the absolute life from strain gauge data, or do simple comparison between damage potentials, between two test tracks or n test specs. Also, we can use fatigue analysis to reduce durations of signals, like in this example here. We've got a long signal, and we may want to cut the sections that are highlighted because they create no damage. We end up with a shorter signal that has, the same damage content as the original longer signal. So that's pretty much it for I would say for time domain analysis. Now we can have a look at frequency domain analysis. Here we're interested rather in the frequency content, typically because we've got modes, we've got modal behavior of a structure of a component, and we want to know whether we are close or not to these modes, for instance. And typically we want to look at also, the distribution of amplitudes over the frequency range, and how is it low frequency, is it broadband, is it etc. So let's have a look at the capabilities in GlyphWorks. First, we've got the classical power spectral density, so it's a global and overall spectrum of a signal showing power versus frequency. Of course, we do have all the FFT-derived spectra, like the amplitude or energy spectrum as well. Also, one can derive the frequency response function that is usually displayed in terms of gain, phase, and coherence, just like you can see on this right-hand side plot. That the gain is in red, phase in blue, and coherence in green here. So starting from an excitation and one or many responses, you may want to calculate these spectra here, showing the modes with their amplification and damping. So that's the FRF. Also, we've got octave analysis, third octave, sixth octave, etc. Here in the plot below, there's a full octave display. We have several filters. One of them is the order tracking filter to follow, to track a given harmonic order, second harmonic, something like this, and you extract the time series, the spectrum from this order. We've got weighting filters to reproduce the human body responses. So we can apply those filters to signals or as weighting functions to the spectrum. We've got custom filters where the user enters the shape of the definition of the filter he wants to apply, and spectrum weighting, just like again in this plot here, we've weighted the octave plot in dBA. Now that we've looked at time domain analysis, a bit of frequency domain analysis as well, let's jump into joint time frequency analysis. So the objectives are essentially, as I said before, to gather information from both the time and frequency domains into one easy to understand plot, but also we want to localize in time and in frequency some specific events, like when did it occur and what frequency did it excite, for instance. So, in terms of time frequency analysis in GlyphWorks, we've got waterfall analysis. So this waterfall analysis glyph was up to version 10 was typically used for rotating machinery. So it would display a spectrogram similar to the one on the top right-hand side of the screen, where you see clearly some order lines, and you can display them below, extract them. So this glyph now in version 10 has been enhanced or improved. A new feature is there to do time frequency analysis. So we'll see the difference between the waterfall analysis for time frequency and the joint time frequency analysis glyph. So these two glyphs can perform time frequency. We'll see the differences. And also we've got the Waterfall Display glyph that displays the spectrograms and has the ability also to extract some slices, whether it's time slices or spectrum slices or order slices in the case of a rotating machinery analysis. And we'll see another feature is got in version 10, allowing to display next to the waterfall display any spectrum or any signal. So that's very interesting. We'll cover that in a minute. Let's start with the joint time frequency analysis glyph. This is a glyph that exists in version 9 and it's been existing for a few years now. We've enhanced it a little bit. It's easier to use now. The increment method, for instance, it's highlighted in yellow here, can be defined as a percentage of the buffer size, and not only in how many points, right? So I've highlighted in yellow here probably the most important properties in the properties of this glyph, which are therefore the increment between buffers and the buffer size. So what happens in this glyph? It will cover the whole signal with buffers, so the buffers advance within the signal, right, with a given increment that the user defines and a given buffer size. An FFT will be calculated for every single buffer. So you may end up with a very large spectrogram, a waterfall made of hundreds, if not thousands, of spectra in some cases. So you may improve the frequency resolution or the time resolution by playing with those parameters. The buffer size, typically increasing it, will improve the frequency resolution, and the percentage increments, typically by reducing it, you will improve the time resolution. So this glyph is something that has always existed in GlyphWorks. Now, as I said before, the waterfall analysis glyph can also do time frequency analysis. This new property called increment method can now be set to x-axis. So typically, if you consider a signal versus time, x-axis being time, this means that this waterfall analysis glyph will do a time frequency plot in the end. And here I also highlighted those two properties. Number of spectra, 100 in this example. This means that the whole signal will be divided into 100 segments, and the output will be made of 100 spectra. So regardless of the length of the signal, or its sample rate, or the number of points, say, generally speaking. So that's quite useful for making sure you end up with a reasonably sized waterfall display. And for each of these spectra can be calculated from n buffers. So in this example, 3 buffers. So in practice, that means that taking this signal into account, we will calculate this spectrum out of those 3 buffers by averaging, for instance, those 3 buffers, and then we'll calculate this next one by averaging those 3 buffers here. So that's the main difference, this averaging capabilities. That's the main difference with the previous glyph. So as a hint here, I would suggest to start doing your time frequency plot with this glyph. it'll give you a very quick overview of the time frequency content, and then if required, if you need to zoom and do a more detailed analysis, you may want to use the previous glyph that will do a spectrum per buffer. Right, so let's make a break a little bit with the PowerPoint, and let's have a look at the software. So let me open up GlyphWorks. So I guess most of you are familiar with GlyphWorks. On the left-hand side, I've got some data. On the right-hand side, I've got my toolbox made of glyphs, what we call glyphs, those icons. And the idea is to associate input data with those glyphs in the working area, in the workspace in the middle. So let's drag this this signal. It's got one channel made of an acceleration signal. It lasts 300 seconds. Let's have a look at its sample rate. It's 512 points per second, so that makes it 160 plus thousand points. So I want to do a joint time frequency analysis of this one. So let's, following the hint I just gave before, let's pick a waterfall analysis glyph first. So for those of you who ever used that glyph, you used to have this speed, typically a RPM signal input given as well. But here, what we will do, going into its properties, we will choose another increment method. It's not speed, it's the x-axis, in our case time. Here, let's pick a buffer size of 512. So we've got one spectrum, we've got a delta F of 1, spectral resolution of 1 Hertz. Then how many spectra and how many buffers? So our signal is 300 seconds. Well, let's divide it into 200 spectra, and for each of these, I want 3 buffers, to calculate each of these spectra. Let's start like this. And I want to display the resulting waterfall. So under display, I'll pick a waterfall display glyph that I connect. And I only need to press play now. Right, here's my waterfall display. So this is nice. It's just, as you can see, slices, spectra one after another. So I may want to have a top view of that. I may want to have, first of all, let me turn the vertical axis in log. Now I want the top view, but before I may want to click on surface display. Now top view. Here is my waterfall plot. So it has 200 spectra in here. What I see is typically where's the energy, right? The energy is rather at the very low frequencies. But at some instance in time, you see this axis here, the vertical one is time, especially in the beginning and in the end of the signal. We see that the energy is more spread up to the mid frequencies. But more interestingly, we see some lines here of energy, very thin lines that go through almost the whole spectrum. We've got it around 100 Hertz and around 100 seconds and around 180 seconds. We've got another one here. So I want to look at these lines. I want to extract the spectrum corresponding at these lines. That's where you can use some slice display that you first need to turn on. So let me turn that to true. I've got now a slice display below, and now it's asking me which slices do you want to display. So let me pick a y-axis slice, and let's try to pick this one. Right. Oh, no, I was almost there. Right. Let's go in a log scale here. Right. And then I can pick another one, another slice this one there. Let's go for this one there. Beautiful. So this one, we see that it's got a high energy at very high frequencies. The first one we saw indeed that it's got high energy throughout the frequency range. I could have done some x-axis slice, like for instance at 50 hertz. I could have asked for looking at the energy or power, right, versus time at 50 hertz. That's another interesting information. So how does the power evolve with time, or the RMS, if you like, RMS squared evolves with time. So this display is quite interesting. Now I've built this flow from scratch just to show you how easy it is in GlyphWorks to perform such analysis. Now, for the GlyphWorks users, you know that I can save that and reuse in the future. So that's what I'm going to do now. I saved a couple of flows for you. Let me just open up this one. It's still a time frequency analysis, but this time we're going to use a joint time frequency analysis glyph together with a report with many displays in there. So I'm using the same signal. Now I want to zoom under around the 180 seconds. You know, there was a peak there. So let's study this peak around 180 seconds. So having this section highlighted means that what's going to come out from this glyph is only this section. So let's press play and let's look at the results. So here I've got a report that shows my time domain section, the corresponding spectrum, and here in the middle the time frequency waterfall display. So we clearly see, sorry, it's now the axes are switched. You know, for this to correspond, we've got the time axis horizontal and the frequency axis vertical. And we see indeed that around, you know, at this very instant in time, we've got the whole frequency range that's excited. However, looking at just the spectrum, you would just see, well, that's a broadband spectrum. You wouldn't be able to tell it's due to only one tiny little shock that occurs at a very precise instant in time. Or looking at the time series, you wouldn't know whether this excites a lot of frequencies or not necessarily. And it's interesting to see this plot because you know where your energy comes from, and you can tell, well, if there is a resonance somewhere around 100 hertz, this shock may excite it. You know, it may be very dangerous for the structure. So that was a quick demo for the joint time frequency glyph and waterfall analysis glyphs. Let's go back to the PowerPoint presentation. Now another interesting time frequency analysis that we have in version 10 is the FRF based time frequency analysis. So what does it mean? Let's look at what it means. This glyph, frequency response analysis glyph, performs FRF analysis. So typically it would output the gain, phase, and coherence. Now in version 10 we've got a new analysis method option in there, which can be turned to waterfall instead of overall. Waterfall means that it's going to calculate spectra at various instants in time, and this the resolution in time is defined by this property here, number of spectra. So I want, for instance, 10 spectra from the beginning of the signal to the end of the signal, and each of these spectra will be averaged from 3 buffers, for instance. So in practice, this means that you will obtain these gain showing modes versus time, this, you know, with this waterfall option. The applications of these are numerous, right? We've got the first one is probably to check non-linearities between input and output, like you're on a shaker and you increase the amplitude of the excitation, the table is moving with higher amplitudes, increasingly with time. And if we were linear, the response on the structure that's fixed to the shaker, right, would increase proportionally, and the gain should not change, being the rate between output and input. It shouldn't change. If it at some point in time it does change, it means that right from this amplitude and above, I see clearly some non-linearities in my structure. So I can no longer consider it linear. Another application is what is the influence of an external environmental, for instance, varying parameter, for instance, the temperature. We know that if you increase the temperature, slowly with time, the structure will see maybe its stiffness decrease or its damping being increased. So we'd expect indeed this FRF to evolve with time. So this would clearly show us how it evolves with temperature, right? Another application is what happens if there is a crack that appears in my structure. Typically, a crack would have the load path to be changed and would result in maybe a reduced stiffness that we could capture either from most probably better with a strain gauge, but maybe also with an accelerometer. And so again, the FRF would see maybe its model, its dominant frequencies to shift, with time, with the appearance of a crack. Another application is some materials soften or harden when they are subjected to vibrations, to cycles. So that would be very easily observed with this new FRF versus time display. So let's do a quick demo of that one. Again, it's very simple, and I've got a flow already prepared for you. So now in input, I've got these signals, an excitation signal, and a few responses. I'm using this frequency response glyph with this new option turned to waterfall. And here I've asked for 10 spectra from start to end of the signal. Let's press play. Here I've got the first FRF between the excitation and first response. So we can see clearly modes with anti-resonances. Then again the FRF between the excitation and the second response, FRF and the third response. So that's quite nice. But let's ask for the top view. Here it becomes clear there's some kind of nonlinearity in here. The natural frequencies evolve with time. They're not constant. That's pretty clear here. So that was it. A quick example just to show how the frequency response glyph has been improved with this additional output for waterfall of frequency response data. Back to PowerPoint. Now we're going to end up with this webinar with the Waterfall Display glyph and its enhancement, which is an additional 2D display. So let's have a look at this. So as we saw before, the Waterfall Display glyph has the ability to extract and display X or Y slices. Now we've got an additional input pipe in there, which can bring an extra 2D display onto this plot. And this 2D display can be a spectrum that I can choose to display on this facet, or it can be a time domain signal that I can choose to display on this facet here, right? We'll see examples of that. But the main applications are like the flow that's displayed here, we may want to display the overall spectrum next to the waterfall of spectra. Or we can observe the influence of again an external parameter like an environmental parameter like temperature on the waterfall. So I could display this time series of temperature on this facet if you see my mouse moving, and see how it influences the waterfall. Let's do some examples. It's probably going to be clearer. So first example is displaying this the overall spectrum. So I've got here a time domain signal. I'm doing the waterfall analysis, time frequency display coming out from here and displayed in this glyph, waterfall display glyph. In parallel to that, I'll use this glyph here that calculates the overall spectrum. Now let me press play. Right, that's what you obtain, the waterfall that we got previously already. But now, in addition to that, I can see the overall. And by turning it around, I can see that indeed, maybe I should put that full screen. I can see that indeed the overall matches the spectrum, right? So it's quite interesting to have this information on the top of the waterfall. Now, just a little detail. For now, this connector is blue only because we figured most users will want to display a time series, and we're going to show that in a minute. So we thought, let's keep it simple. Let's keep it a blue input. This overall spectrum is given as a histogram. For those of you who know GlyphWorks, the blue pipe is blue connectors are dedicated to time domain signals, whereas the red one are typical of histograms or spectra. Well, in version 10, we've got a type conversion glyph, which is dead simple to use, right? Input, output type. So it turns the information driven by the red connectors into information driven by the blue ones. That's as simple as that. So that may be a very useful new feature in the software. Now let's have a look at the another example, still to do with this extra display on the waterfall plot. Now we've got an acceleration data. That's an example coming from the automotive world, together with the speed of the vehicle in kilometers per hour. Let's first split those two channels. The condition being anything that has accel in its name. So this, the channels following that condition will go out in this pipe, and the other ones will go in this one. So here we've got the acceleration data. I do a waterfall analysis, and here I've got the vehicle speed data that will be displayed on the top of the waterfall. Let's have a look. Right, that's my waterfall display. And you can see the speed profile displayed next to it. And what we see is the relationship between the energy and the value of the speed. As we would expect, once the speed reaches 0, we've got no vibrations. That's fine. But what we see also is that where we've got high frequency energies, it's typically when the speed is very high, like typically when it goes up, when it goes above, when it goes above, say, 75 or 80 kilometers per hour. That's where we've got those high energies, those high frequencies. Energy in high frequencies. So that's just an example. I'm sure you've got all in mind some better examples to do with pressure, temperature, or any other external parameter that could help understanding what's going on on this vibration data, and how is it related to some event or something that happened during the test. Right, some conclusions. So GlyphWorks, I think, has quite a few capabilities for time frequency analysis, and we're constantly adding new features. And at this release, version 10, we added quite a few interesting ones, especially to do with time frequency analysis. We've got, we presented this waterfall analysis glyph, which has been enhanced to allow time frequency analysis, and this can be used for a quick overview. As you could tell, it's very fast, very quick to get a fast overview of what's going on. Now, if you want to go more into detail, use the joint time frequency analysis. If you want to check for nonlinearities in your model responses, model data, the frequency response function glyph has been enhanced to allow waterfalls of FRF, as we showed before. So that's a very interesting feature as well. And finally, the waterfall display has now this extra 2D data that can be displayed on one of its facets. So